All right. Hello. Today I've got something interesting. Well, I think it's interesting. This is a question that I was asked by Avery Sumner, one of the DLU devs, and it's a genuinely interesting question to talk about. So, to begin with, let's think about. Really should have thought this one through. Come on, what's a good example? Okay, yeah, let's look at one of those flashing neon lights. It's maybe something like this. Oh, you can tell how good I am at art. Yeah, look at one of those flashing neon lights. Now, you go years ago, people probably like, magic. Eventually, we kind of realised, okay, something like lightning, like you activate it by passing a charge down. But what happens if you want to make more informed predictions about it than that? Well, you have to start modelling things differently. So the next model you'd probably think of, this is in no way to scale, would maybe look something like this. You've got a some number of electrons. Again, these are incorrect as numbers of electrons go. I forget where neon actually is in the periodic table. So I'm just going to guess its outer shell looks something like this. It may not. It may be 18. I don't remember. But anyway, so this is then the next thing. So here we've got these little things called electrons for negative charge. And we've got inside here, we've got some things called neutrons, which have no charge, and protons, which have a positive charge. I'm concerned writing it like that may actually denote a positron, but anyway, I mean protons. And these are small things. These are small things held together by something known as the strong nuclear force. And if you're anything like me, you may be wondering, okay, people are mentioning this strong nuclear force. For starters, seriously, that was the best name you come up with. Secondly, okay, how does that, what does that force look like? How does it, it's like gravity, we have a formula. It goes F equals G m1 m2 over r squared. And you may ask, what does the strong force look like? And there's no formula like that, unfortunately. It's basically way too hard to calculate a formula. I'm trying to come up with a good reason why there isn't a formula like that, and a way that will seem understandable. Basically, there more or less can't be. I think we might get onto some of the stuff to do with that. We'll do with why that's the case, but effectively, it is just a question that is too hard to solve. Like, you can prove that there exists almost all of the time no general formula that looks anything like that. And we might see a bit about why that is later on. So now we're going to take a little bit of a look at this proton, because we start noticing is, well, this thing called radioactive decay. Some weird stuff goes on there. We might get a neutron going to a proton plus an electron. I've not conserved lepton number. I don't remember what leptons are. Something like that. Oh, plus an electron anti-neutrino. That's it. It's been a long time since I've done particle physics, so the particle physics side of this may well have huge issues. But anyway, so this is a decay. I believe this is mediated by weak nuclear force. I don't remember off the top of my head. And so this is a little bit interesting because, okay, these two things they're both what's known as leptons, I think. No, that's a lie. They're known as fermions. I think these two are leptons. You can tell it's been ages since I've done particle physics. Is the contrast between leptons and No, it isn't. I think they're both leptons and fermions, and I think what I'm thinking of is hadrons. As I say, it's been a long time since I've actually looked into the classification of any of these things, and it doesn't really matter for what I'm going to go on to say here, which is basically that if we look at these two are one sort of thing, and the electron anti-neutrino is kind of just there to balance out the electron. The electron is there to balance out the change in charge as the neutron goes into a proton, and then this just balances out the remaining. And those two are kind of a similar thing. I'm fairly certain it is lepton, and I think these would then be hadrons. Again, don't remember if I'm getting this right. Doesn't matter. Because the interesting thing is that these two are quite similar. Oh, great, now I've got to remember stuff about quarks. Oh, no, okay, this is annoying. So, the point I'm trying to get at here is the smaller and smaller we go, or sorry, is the more predictions we want to make, the more things we want to understand, the smaller we need to go. So, at some point, we might realise that, oh, actually, we need to begin considering, in order to understand how these behave, and we don't actually really need to understand how these behave, but if we're looking at these two, actually maybe if we're looking at these two, we might start noticing some patterns. In particular, you can consider a set of things that look quite like this and start mapping their properties, and you find that it has, if you consider like a variety of particles, you find it has some kind of hexagonal structure. Neutrons in the center, proton and antiproton being like here, that would be plus, minus. These are probably pions down the sides. There might be a kaon somewhere. I think kaons involve strange quarks, and they're what's on this diagram. But the point is, you get this rather interesting structure. And the way this structure is explained is using something known as quarks. So a neutron is made up of an up quark and two down quarks. They might be at this stage, I genuinely don't remember. It has been so long since I've done this. I think down quarks have a charge of -1/3 each. Maybe it's anti-down. I don't remember. And then, so this charge sums to 0, and you then have protons, which have a charge of up, up, down, and that then's 2/3, 2/3, -1/3, and that sums to 1. And so, hey presto, we can, and combining these in different ways is then actually what explains the shape of that hexagonal chart. And so the question I was asked was this. We started off on the scale of our neon tube. We then went down to the scale of, well, I guess to begin with, we just go down to the scale of an atom. Then we go to the scale of an atom as, okay, this actually now has electrons orbiting a nucleus. Again, if you're anything like negatively charged electrons orbiting a positively charged nucleus, again, if you're anything like me, you might be complaining now that, well, actually, they're not really orbiting. That's not quite what quantum mechanics tells us. And I know, but it makes no difference for the point I'm trying to make. As we zoom in on the electrons, nothing really seems to change. If we zoom in on the nucleus, we suddenly see that the nucleus goes to a series of neutrons and a series of protons, all bound together very closely. And as we move on, as we zoom in on the neutrons and protons, we see that actually each neutron and proton is made up of 3 quarks, even more tightly, closely bound together. All right. So, the real question then is, what comes next? Because at every point on this diagram, we've thought we've known what the next step was going to be. And so, the question that Avery asked was, do I think we will ever find something smaller than a quark? And that's what I'd like to answer today. I began attempting to answer this in some form by writing a huge text wall, and I decided, if I'm going to all the effort of writing that text wall, let's do this in a way which other people might get to hear about and stuff. And so yeah, we're going to look at this. So firstly, the first answer I came up with was honestly just a little bit of a sarky answer, which was we know. So there are different contributions to the mass of a proton. One contribution to the mass of the proton, this is actually the main contribution, is simply from the energy stored in holding it together. And via E = mc², rearranging this, we can see that there actually is a contribution to the apparent mass of the proton due to its energy. This turns out to be most of it, but importantly, it's a calculable amount, and we know the mass of a proton. So by subtracting the mass of the energy from the mass of the proton and dividing by 3, we can work out the mass of a single quark. And I honestly don't remember what this was. I want to say it was on the order of mega electron volts. Could be wrong, could be misremembering. That seems high now I think about it. So I really don't remember. So to like kind of give a snarky answer to the question, well, the answer is yes, we already have something smaller. I did the Electron Anti-Neutrino earlier. That I believe that's incredibly light and is, I believe, on the order of like 1 electron volt, something like that. It's not far off. It's, I believe, significantly less massive than the quark. This was from a quick Wikipedia search. Frightusy asked me the question, and I could be wrong. But there's something more interesting to this question, because, well, there's an obvious answer. There's an obvious, like, sci-pop answer of, or pop-sci answer, I guess, popular science answer of what happens when we go smaller. What happens when we go smaller than what we understand? And the answer I might have given was the following. Great, how do I draw this? Yeah, let's go something like this. What I'm attempting very badly to draw there is a string which is wrapped in a circle, which is moving back and forth, which is oscillating. This is known as string theory, and string theory is a brilliant piece of maths. In fact, it's such a brilliant piece of maths that the guy who did it basically won the Nobel Prize for Maths. I say basically won the Nobel Prize for Maths because, as many of you all know, there is no Nobel Prize for Maths. In fact, what you have instead is a medal known as the Fields Medal, which is the equivalent of the Nobel Prize for Maths. And it's quite interesting. Why is this the case, one might ask? And the reason is that string theory, honestly, people who know more about me may argue than this, but just judging by what's happened since string theory was first theorized, it's not a hugely testable theory. There are the two things you like to have in physical theories. One is predictive power, and the other is falsifiability. If someone comes up with a physical theory, what you should ask them is not only what does it predict. Well, I guess they're kind of a similar thing, but specifically you should ask, what ways can I disprove your theory? And they should have an answer for that. And the issue of string theory is that, well, there isn't really a way to disprove it. Okay, there are, in theory, but like I believe it's a subset of string theory I think that's how this works. Again, I'm no expert on these topics, but is supersymmetry. And more or less what supersymmetry has us looking for, it says at the moment is, okay, I'm going to make some predictions about other particles which might exist. Now, those particles are all way too massive to be detected by the Large Hadron Collider. So you're going to need to build a larger one. And you're going to need to keep building larger ones. And kind of there's been something of a falsifiability crisis with these things where it's really hard to prove them wrong because, well, the issue is they're trying to probe something known as quantum gravity. And I'm so off topic for what I meant to talk about, but no, that's what this was I knew this was going to happen anyway. Quantum gravity is kind of the question, well, one could say anyway, it's a question of what happens if you have an incredibly small black hole. Or what happens quantum mechanically near the surface of a black hole. There's stuff like that, various things you can rephrase. The issue with quantum gravity is that, well, it's really hard to test. Our first theories actually were provably and the first quantum gravitational theories were almost provably non-falsifiable, in the fact that the universe as we know it is kind of ruled by a series of constants. I'm going to write the Boltzmann constant in brackets, actually. I'm not writing the speed of light on here, because the speed of light is actually created from combining these two. What other constants do we have off the top of my head? Wow, how can I not remember any more? I don't think the Stefan Boltzmann constant is. Okay, the constants just aren't coming to mind right now. Yeah, here we are, H bar at least. So these are to do with electromagnetism. This is to do with the scale of quantum mechanical effects. There are more, which are not coming to my mind for some genuinely concerning reason. But anyway, we've got these important... We've got this set of important constants, and the lovely things about these is we can measure them. And the reason we can measure them is because there's a finite set. What if I gave you the following? I gave you 3 points, and I asked you to fit a quadratic to them. Well, you may or may not know what a quadratic is or what it looks like. It's a function that looks like this, more or less. That's a reasonable quadratic. And you'd find that actually a quadratic can be written in the form ax squared plus bx plus c. And note, there are 3 points here. I've constrained my equation in 3 ways. And that's quite nice, because as it turns out, I can then just write it using this. In those constraints, tell me there are three unknowns in this equation, which are constrained by my 3 variables. But what if I instead told you that, oh, actually, you've got those 3 things, but the model you need to fit actually looks like this. Then you'd have a problem, because that is a cubic, and whereas before there was only 1 quadratic I could draw, there are actually, you can show, infinitely many cubics which satisfy this equation. People might argue what I'm drawing now aren't actually very good cubics, and they would be right. But there are an infinite number of these because I've only given you 3 data points, and here there are 4 unknowns. And therefore, with the number of measurements you have here, it is impossible to determine all of these. Because I could always change A, I could make A whatever I like, and there would always be values of B, C, and D, which would give me a fit to all those points. Which is... it seems like a little bit of a tangent. Okay. Which seems like a little bit of a tangent. But it isn't. Because there's something... because this was the issue of, like, the first attempts at quantum gravity, was the fact that, effectively, it introduced more constants than we could ever hope to measure. And you might think, okay, well, surely, Ninja, if you just make enough measurements, that'll be fine. But the issue is it introduced, like, an infinite number of constants. And, well, we can't make an infinite number of measurements. Which was a bit of an issue. I would argue, actually, there's that's not necessarily a reason the theory's wrong. There is no reason to assume that, actually, we should be able to predict. We should be able to make a physical theory. Like, there could be an infinite number of undetermined constants. There's no fundamental reason why physics should be predictable, but we really hope it is, because, well, if it isn't, we're out of a job. And so what we have at the moment is we have a graph which kind of looks like this. Over in the left-hand corner, we have classical mechanics. This is at... I forget what, like, rigorously these axes should be. Which is annoying. Okay, which is... so it describes things which are relatively... I think there are just different ways of phrasing this, so I don't think I'm necessarily wrong, although someone may choose to disagree on that, and fair enough. Feel free to leave any thoughts or corrections on this in the comments. So over here we've got classical physics, and this is when our things have quite large mass, or if I'm being more accurate, they're made of a large number of massive particles. And over here we have... and it's relatively low speed. And so this gives us, I'm using V for speed, classical mechanics. I was just going to write classical mech, which is why I spaced out as I did and then began writing mechanics. Over here, as we suddenly start increasing the speed, we have relativity. And I'm realizing as I'm drawing this diagram that I'm kind of wrong. And so this is true as long as your masses aren't too low. Meanwhile, if your masses get very small, or you're dealing with, more accurately, single numbers of particles in a very controlled system, then you get quantum mechanics. And I realise as I'm drawing this diagram that actually we do have a thing for the final box here. It's quantum field theory. But the point is that classical mechanics is, in a sense, it's just an approximation to relativity. It's a pretty good approximation in our day-to-day life. As long as V is much less than C, then this works really well. And as long as if I'm being completely rigorous, it should be as long as the action S of something you're doing is significantly less than h bar. But as long as you're dealing with relatively small energies, small masses, small timescales, then quantum mechanics holds. But again, classical mechanics isn't wrong. It's just, it's a limiting case. It's like saying, well, I've got a mountain outside my house, and saying that I cannot take the first step up a mountain because I don't know what all of the mountain looks like. Classical mechanics is the equivalent of just taking small steps one at a time. And as long as you're not moving too far, the overall size and shape of the thing doesn't matter. What matters is how it behaves within a very, very small region. In this instance, what matters is the region of very, very small speeds, and we live our life in very, very small speeds. So I don't need to know. A better example might actually be that we've got like the cloud line up here at the top of our mountains. But in order for me to live my life, I don't need to have trained to cope with the oxygen concentrations at the top of Everest. That's perfectly fine. All that matters for my day-to-day life is how the world behaves in this really limited region in which I live. And so that's effectively those are effectively the differences we have here. All of these are limits of the others, or rather, classical mechanics is limits of relativity, and quantum mechanics, both of which are limits of quantum field theory, or QFT. But there also exists something else, which is the limit of large mass, or of equivalently strong space-time curvature or large gravitational fields. And the issue is that QFT is a limit of that, but we don't know what the full theory is. We have quantum mechanics and general relativity, and that's like, they're like two things here. They're both true in a sense, but we don't know what's here. But the issue is that general relativity requires you to be dealing with very strong gravitational fields, or very high masses. I don't really know what it's large relative to, but very high masses. Or it requires you to be, or equivalently, because E equals mc squared, it requires you to be dealing with very high energies. Meanwhile, quantum, or very high velocities as well, and quantum field theory requires you to be dealing with like individual particles. Or okay, I'm being a little bit glib, but anyway, the point is that it's really hard to answer the question of quantum gravity, which is what stuff like supersymmetry is trying to answer, simply because the region it exists is so hard to reach. Relativity doesn't matter to us because we're always at low speeds, or we're always at the bottom of the mountain. Quantum gravity is so hard to measure that it's so hard to measure solely because, well, we can't climb physically to the top of the mountain. We don't have the tools to get up there. And so, yes, I just randomly drew a circle there. I was going to do more, but it just ended up being a circle. And so, And so I was going to answer a question about what I thought was smaller, and okay, this is all related, but it's interesting how much of a tangent I managed to get off on. But this is the issue. I came onto this because I was thinking about supersymmetry, and the reason I was thinking about that was because of string theory, and it's the idea of predictions of extra particles. And so there's the question as to, well, effectively, do I think extra particles will be found? Now, if supersymmetry is true, then, well, actually, supersymmetry, also known as Susie, if that is true, okay, I can't believe I'm going to be saying this video to Avery. I know exactly what he'll comment at this stage. But anyway, if I really shouldn't have done that. But anyway, if supersymmetry is true, then it does predict a ton of extra particles. And there's a question, will those particles be smaller than a quark? And the answer is no. If supersymmetry is true, they won't be. In fact, supersymmetry, the reason it's so hard is because actually all the particles they're predicted have quite big energies. Their energies are really, really hard to achieve. And that's the reason it's so hard to test, which is the reason why I doubt supersymmetry will ever give us something that is smaller in that sense than a quark. And personally, I feel like string theory, well, I honestly feel as though supersymmetry and string theory may never be tested successfully. I feel like they may always keep predicting more things. It may be the case that one day they are tested successfully, but there's currently not a huge evidence to support them. A huge amount of evidence to support them. They're lovely theoretical frameworks, but the evidence isn't really there. So, where do we go from here? Well, that still leaves a fair bit of wiggle room. So, do I think that, because it doesn't have to be necessarily going this way. There are unsolved problems in physics. There is the question of the arrow of time. Why does time appear, why do we perceive time as flowing forwards when all of our equations suggest that, well, actually, it doesn't matter which way we go. All our equations are time reversible, and more or less there's something known as CP violations, which also violate time, symmetry, but those are on a very small scale, and I doubt they relate to our conscious perception of the world. We also have other unsolved questions. Why is there an apparent lack of antimatter in the universe? I say apparent lack because I'm still not convinced it couldn't just be elsewhere. There may be a very good reason for this. I don't know enough to know if there is. And there are... I'm running out of time. I knew I would not have time to finish doing this. I've barely even begun to introduce the ideas I plan to discuss. It's not going well. I know, I've just lost my train of thoughts. No, this is not good. I cannot be losing my train of thought on this. What was the last thing I drew? Yes, oh, actually, that saved me. It's amazing. Unsolved questions. There are time reversal, symmetry. There's questions as to the wave function collapse in quantum mechanics, and that's not well understood yet. Why do we suddenly go from a particle who may be somewhere here to a particle which is suddenly in a single incredibly sharply peaked position when we measure it? Why does this happen? Why do we have this operator that seems to go from one state to another? Why is this all happening? We don't have an answer to this. But there's something... And so, yeah, there is definitely room for physics to change. I personally doubt it will be in the supersymmetric direction. I don't know if it will come from there, but there is room. And so there's a question of... The question then becomes... Well, we had the question, do I think a new particle will be discovered? Do I think a new particle will be discovered that is more fundamental than a quark? Do I think that by actually looking more closely at quarks, we might realise that, wait a second, because there are different types of quarks. As you saw before, there were up quarks, down quarks, there are top quarks, bottom quarks. There we are. Strange quarks and charm quarks. Those aren't actually in the order most people would write them. I believe strange and charm would be the other way around, but Doesn't make a huge amount of difference. Point is, there are quarks, and hey, maybe these quarks have properties that can be more simply explained. They can be more simply explained by exchanging them. And what I'd like to argue today is that it is meaningless, at least with how we currently understand physics, to say that a new particle will be found. And I mean that as in, I can answer Avery's question right now by going, what do I have nearby me? Okay, I've got a, I was just about to pick something up. Obviously you can't see that. I'm going to pick up a saucepan. It's my amazing drawing of a saucepan. I'm going to go to my kitchen. Gonna put it on the hob. Just going to go on. It's an induction hob, so I don't have to draw anything too complicated. And I'm going to zoom in. And when I zoom in, I will find that within this piece of metal, I have something strange happens. Well, it's not strange. It's kind of logical. What happens is that I have lots and lots and lots of waves moving back and forth in the metal. What I mean by this is that imagine I have a series. Let's say I've got a slinky. I can imagine a slinky as being a mass connected to a spring, connected to a mass, connected to a spring, connected to a mass. There's a limit to how much we draw this out. Connected to another mass. This is a reasonable model for a slinky. And you know that I can... Well, okay, you possibly don't know that I can, but I'm going to promise you that I can. But you'll be aware of the idea that, yes, waves do travel back and forth along a slinky. If I do this, then I'm going to get a wave that propagates along at some speed c. That's brilliant. It's going to move along my slinky. And as it turns out, atoms in a metal, as long as they're not moving too much, or let's say atoms in a metal, could say electrons, doesn't make much difference. I'm just thinking, I have this issue of trying to be too exact. It doesn't really matter. What matters is that in a metal we have things, and these things tend to exert Coulombic attractions on one another, which means they'll be attracted. Well, actually, no, Coulombic repulsions on one another. It means they're going to be repelled, and they're going to be repelled in the same way gravity was attractive, actually, like 1 over r squared, where r is the distance from the centre of the particle. So, really, I should have more accurately. Yes, I'm aware all my r's are looking like n's. They're normally a lot better. I don't know why. And so if I've got 2 particles here, I can work out the force between them. It's going to be repulsive. But the thing is, I've also got a second particle over here, and that's also contributing. So you get to have more ninja because yeah. Well, I guess it's not more ninja for you, but yeah, the video that was a cut. See me being fancy and doing cuts. I'm going to redraw these R's because they're annoying me. Yeah. So basically, we've got one particle in between 2 other particles, and both of those are going to repel this one. And we know exactly how it's going to repel. You're going to have a 1 over r squared coming from each one, so it's going to be something that looks like that. Well, I've got to be a little bit precise about this. Let's just define this point as 0. I'm going to say this direction is x. Yeah, that works. This is at the position r1, so the position r2. Why am I bothering? This is a little over the top, and the force may be in the wrong direction, but hey, it doesn't really matter. I guess both those would be squared, in which case the rearrangement I thought I was clever for pulling, I'm not. Bit of a rip. So yeah, anyway, the force is going to be something proportional to that, which I can do stuff with. However, it's a little bit annoying because that's not the neatest form that force could be in. And in particular, when I start considering loads of these all next to one another, that actually becomes analytically unsolvable. Even with actually 3 of these, it already is analytically unsolvable. It's known as the 3-body problem. The 3-body problem was originally a problem from in astrophysics. It was dealing with 3 bodies orbiting, Newton being like, I'm kept awake by the fact that the moon, and that I can't work out how to make the moon, Earth, and Sun all work. You can tell I'm good at this. Anyway, fortunately, this can be really quite simplified down by the fact that, well, we've got kind of these, okay, they're not actually connecting up, they're adding up, but this particle exists being repelled by those 2 things, and more or less we can say that, assuming it doesn't move too far, we can find a spring that does roughly the same thing. So for a spring, the force, yeah, what I've drawn here isn't actually a force; it's a potential. So it's as though this particle were this were like a hill, and the particle here is the force it feels, were as though it were rolling back and forth on a hill that looks something like this shape. And so what I can say is, rather than having a hill that looks something like this, I'm going to take a slightly simpler hill that looks something like this. This is going to look weird and stupid. I promise you there's a point to this. Because this is going to want to... This is effectively the energy, or the potential energy the ball has, and if you had a hill that looks like adding these 2 potential energy curves up together, it would look something like this. But at the bottom, and like these go off, I think part of the issue here is my drawing, these go up incredibly steeply. Here, this is a parabola. It's the same shape you get when you throw a ball. And this is, rather than the force between 2 charges, this is the force between something on a spring with a wall. Let's put it as 2 springs because it makes it nice and symmetric and a little bit more obvious where the relationship is. Now, if you keep going further and further off, this is they're gonna not match up very well. But as it turns out, the only important thing is this bit right at the bottom. And as long as you pick your springs in the right way, and you don't give your particle enough energy that it can, like, go too far up, then it's only ever going to be in the bottom. And as long as it doesn't move too much, well, you're not going to be able to tell the fact that this goes up incredibly steeply over here. You're only ever going to see that bottom bit, and that bottom bit is more or less identical. And so, with that simplification, we can turn the molecules in my saucepan into, or the atoms in my saucepan, into a series of springs, a series of particles on springs all connected to one another. And you may ask, what's the point of this? What's Nietzsche going on about? Well, it turns out that this is actually a relatively interesting equation to solve, in the fact that we can solve it. We couldn't solve the previous one, but we can solve this one. If I were to write something that wasn't this equation out, it would look something like this. This isn't precisely the equation that it obeys, but this is a far more famous but related equation, which is this. This here is, if I were to make the distances between each particle smaller and smaller and smaller, tend that towards 0, then I would get this equation. And this equation is really, it has some nice properties. It's known as the wave equation because it's what gives rise to, okay, not water waves, that's a really bad example, but it's what gives rise to waves in physics. I mean, water waves still are an example of something related to this, but they're just a bit more complicated. But this is what gives rise to light, for instance. Light is the most obvious example. But sound waves as well, they arise from an equation like this. Again, the equation is slightly different. For sound waves, it's a similar sort of thing. It works as long as you're near the bottom, and Thank God it does, because otherwise we wouldn't be able to hear sound, but it doesn't work in general. It doesn't work in particular when the amplitudes of the noise get very, very large. But that's fine, because realistically, they actually don't really. I said that completely unjustified. I don't know the maths. But the point is that equation has a really, really useful property, and that property is linearity. It shares this property with light, which is the reason why. Well, what is linearity? Linearity means if you have an equation and you have one solution to it, let's say I've got a light ray travelling in this direction. Okay, maybe it's spreading out a little bit, or maybe I've got it from a laser. Well, yeah, I'd say it's spreading out a little bit, and I've got light rays travelling in this direction. Wow, that was a terrible light ray. I've got light rays travelling in these two directions. Well, either of these can happen on its own. I can have that, or I can have this. But another valid solution is the two of them together. And the important point is that you're just superposing them. You're just adding the two up. And you don't get anything different. The photons don't come here and then bounce off of this photon and say maybe, I don't know, maybe this one bounces off back here or something like that, and this one bounces off up there. I mean, not conserving momentum, but it doesn't make a huge amount of difference. The point is, they don't interact. And so what we can do is we can take these, we can take these springs, and things which look a lot like waves. As mentioned, they're only waves when you make this distance incredibly small. But these things are incredibly similar to waves. They're just waves which are a little bit more spaced out. Now, this is interesting, because at this stage, we've got a solution to the equation. However, and this describes some things relatively well. It describes why things conduct, to some extent, because I can have a wave propagating in this direction, and that wave is going to have vibrations of molecules moving backwards and forwards, and each one's going to move some energy onto the next one in the chain, and you're going to get conduction. You're going to have energy propagating along this chain of atoms, and it's brilliant. We can solve for that. The issue is that, well, I did make an approximation. I said that the potential, which is like incredibly... I'm having difficulty not drawing a quadratic. Potential that's incredibly sharp, like this, was equivalent to a potential that was far less sharp. Like, for instance, this. And that works as long as they're not at the bottom, but sometimes maybe you put in enough energy that they move out of the bottom. And this is where things get quite interesting, because suddenly, when the second you're no longer at the bottom, the second you're maybe up here, suddenly that superposition principle, the reason why photons could pass through one another, like this, well, suddenly that doesn't hold. Suddenly we do go back to that situation which we didn't have for photons, where one can bounce off the other, or at least where the two can interact. Which is interesting, but I just said it wasn't solvable in this instance. And so, in the instance where things went too far, I said we made this simplification because this on the left wasn't solvable. So why does it... I'm talking about collisions, and we know these occur. They're really important for how these metals behave, but, well, they don't occur. And this is kind of the point I've been getting onto, because the way we can begin to work this out is something known as a perturbation theory. If you're interested in quantum mechanics, you may have heard this term. You may have heard quantum gravity being described as non-perturbative. And what this effectively means is that we can look at a series of things that can happen, and we can assign them a likelihood that they will happen. So, for instance, these two hitting and going off into these two, well, that's a reasonably likely event. It's certainly much more likely than this one, hitting this one, and going off like this, and that one shooting off loads to conserve momentum. One's, I should have had at least something going upwards, but it doesn't really matter. One's significantly more likely than the other. And so what we can do is we can literally construct a series of these effects. We can enumerate every single possible effects that could happen from the really simple ones, well, from the most simple one, which is they go through, don't interact at all, then getting progressively more simple, or progressively more complicated. Maybe they do something like this, then getting even more complicated. Okay, now this time we have three hitting one another, and they go off into this, and this. And this is the only way we can even begin to solve this equation. But notice something really strange happened here. I suddenly moved from talking about waves, a wave, something that looks like this and moves in one particular direction. I suddenly talked about waves bouncing off of one another. But what does it really mean for a wave to bounce off another wave? Like, that doesn't make sense. The only way we can make sense of that is if we treat a wave as something like a particle. Because what does it mean for something to bounce off something else if, well, both of them are continuous? So what we say is, what if instead of having a nice... I should actually do something a bit more like this. That now just looks like a spring. I should draw it curvy. What if instead of having a nice continuous wave like this with a pretty much constant amplitude, constant up to a factor of my drawing, what if we instead dealt with a wave that looked slightly different? What if we instead dealt with a wave that looked something... Sorry, that should really be dotted. For consistency, what if instead we looked at a wave like this? Suddenly, this wave is local. And because this wave is relatively confined to one space, we can track the peak of this. We can see where this peak moves. And what we can do is we can treat this as a particle. And you can show that if you take loads of these waves, and if you add them all up, you can make any wave. And so, by looking at a wave in this way, by like localizing it, the way you localize it, by the way, is add two waves of incredibly close frequency, or potentially add a lot of waves of relatively close frequencies, depending on how rigorous the particular maths you're doing demands you be. What we can do is we can express our waves as series of particles. I can have this, but I can also add an extra wave here. And I can add an extra wave that's a little bit further ahead. And I can add all of those up, and I can send a series of these particles one after another. And every time these particles will have the option to do one of those things, or maybe they'll have an option to do the next one. But the further along we go, the more particles have to be involved for something to happen. But the more particles that have to be involved for something to happen, the less likely it is to happen. The things we're talking about here aren't precisely probabilities, but the intuition is the same as if they were. The point is that the further along you get, the less important these terms are. This is notation in maths means it's of the order of this at the most. Any contributions after 4 are going to be significantly less. And therefore we can describe the behaviour pretty well by considering just the first couple of steps, and these are what are known as Feynman diagrams. But this is quite interesting, because we started off with something that was in no way a particle. But in order to come up with some way of making sense of how a really complicated system interacted with the world, what do we have to do? We had to treat it as a particle, and we had to sum up its interactions, but that's incredibly strange. All we had here were atoms. next to one another, vibrating back and forth. And somehow, doing the maths, we got a particle. And you may be thinking, Ninja, this is stupid. You don't have a particle there. This is completely... You haven't invented a new particle. You said you were going to invent a new particle by doing all this, but you haven't invented a new particle. You've just said, oh, hey, the maths checks out. You gave no proof of that. There is one, by the way. But you just said the maths checks out a lot more nicely if you did the certain thing, right? But that doesn't mean that's real. There isn't a particle there. It's just things bumping into one another. But that's all particles are. I'm not going to say precisely things bumping into one another, and I'm not going to say that that is reality or that is true. There's an amazing quote, or there's a quote from an amazing professor at MIT, Professor Adam Adams, who did a brilliant series on quantum mechanics, and he said something that you'll probably have heard some variation of if you ever study quantum mechanics, because quantum mechanics is the first time you're asking the why. You start asking the why questions about physics, or the ones where there isn't an answer to them. And he said something along the lines of, if you see a theorist, and you see this theorist proclaiming something to be true, you should go up to the theorist, and you should enact some form of well, I'm attempting to draw a boxing glove here. You should enact some form of violence upon this. It was a slightly gendered form of violence. You should enact violence upon this person. I would correct no matter what gender they are. The point he's trying to make is that physics does not explain truth. Physics has never explained truth. All physics has ever been is a model of the universe. Physics does not aim to tell you what the universe is. It does not aim to tell you what the universe does. It aims to make predictions about the universe. The reason this question comes up is because people start seeing equations like this, and I'm going to get a sign convention or something wrong here because I know it will happen. I should have started drawing this equation a little bit earlier so I could keep up the momentum I had there. It's really quite disappointing. There's a factor of plus or minus I, depending on your sign convention. Doesn't make any physical difference. People see an equation like this. This is the equation that describes quantum mechanics in the simplest of senses. And people see an equation like this and be like, okay, where does that come from? And depending on the lecture you have, you may get some answer of, oh, well, these terms each come from... we move to operators, and these operators, we know certain things behave. We know that waves behave in a particular way, and they may write out an equation like this, and they may say, okay, we're going to have momentum operator acting on this, and it needs to give us the momentum. And okay, this is the fact that I'm mispronouncing this is I've accidentally fallen into the trap for me because I'm trying to talk quickly and excitedly because I am excited. And they're like, oh, to make the de Broglie relations work, we need to know that for plane waves, this P operator needs to take a form that looks something like. Did I actually get that right? I think I did. I didn't really expect that to happen. We need to know that P, this thing constant between these two equations, looks like this. And you can then ask, okay, but why do the de Broglie relations have to be true? And you can keep asking these questions, and they're like, well, an alternative way of arriving at these relations is by, if you take the Lagrangian density of a system, you know it has to have some certain properties. In particular, you know that it has to have translational invariance, and you can do this, and you can make some argument that this is equal to the Lagrangian density elsewhere, and you can keep building this up. But then you can ask, why does that have to be true? Why does the Lagrangian density, why does the universe have to be translationally invariant? And, well, maybe this person can come and give you some logic that states that, well, physics, by definition, the laws of physics have to be predictive. They have to be applicable no matter where you are. But then you can say, well, if that's the case, why do we have special relativity, which comes from a different type of invariance of the Lorentz? And you can keep asking these questions, and you can ask more and more of these questions, and you will find eventually, no matter who you're talking to, that they eventually will give you the answer, because that's what it seems to do. That's the fundamental point with physics. All we are saying is that this seems to happen. This equation that I wrote before, I'm going to go back because it took a little while to write it out. This equation that I wrote before, it is not true. I can't go back that far. That's a shame. The equation that I wrote out, that was the Schrodinger equation, by the way. That equation is not true. There is no truth in that equation. In fact, we don't really fully understand what that equation means. That's known as the measurement problem of quantum mechanics. We don't know what this means, but what we have is something that lets us do a arguably quite magical thing. It lets us predict the future. But it's just a model. We don't know why it's true. No one knows why it's true. Or at least no one can prove rigorously why it's true. You could argue that knowing is something personal, and therefore a belief felt strongly enough might count as knowing to you as a person, but there has been no proof ever provided to the scientific community which has explained why physics should be true. Fundamental conceit of physics is that it is true, and it isn't. We have no way of showing it's true. All we have is a way of showing that something describes the world well. And so you may be sitting here like, okay, Ninja, you've gone through all of this, right? We get your point. Physics is just a model, but surely there is something more to these electrons and these gluons than, like, these aren't just approximations to waves that we do to make the universe seem nicer. And the issue is that isn't true. I mentioned Feynman diagrams earlier. Feynman diagrams come up in the diagram I drew a bit earlier. I drew it. We have quantum mechanics up here. Sorry, no, that's not right. We have classical mechanics up here. We have quantum mechanics here. We have relativity here. Or let's say special relativity, to be specific. We have special relativity up here. And down here I wrote this mystical thing called quantum field theory. For those of you who know what quantum field theory is, why on earth have you been watching this video? For those of you who don't know what quantum field theory is effectively the unification of quantum mechanics and special relativity. And what quantum field theory says, well, let's first bring out what quantum field theory does. What quantum field theory does is make predictions about things that I mentioned earlier on, about the strong force. It makes the prediction as to why protons, two things which are both positive and which should, by all rights, repel one another. I've talked a lot about how like-charged things repel. I haven't used those words. Like-charged things repel with 1 over r squared. These things should be repelling one another hugely, but for some reason these things don't. For some reason these things stick together. They stick together in an incredibly tightly bound clump. This clump typically being on the order of, well, an atom might be on the, or okay, interatomic distances might be on the order of 10 to the minus 10 meters. The center of the nucleus, that's on the order of 10 to the minus 14, or maybe even 10 to the minus 15 meters. That's incredibly close for things which repel one another more the closer they get to be confined. How do they stay together? Well, they stay together through this thing called the strong force, which I mentioned. But the strong force, I said earlier, how can that overcome the 1 over r squared? Well, I said earlier, there's no formula I can write for that. Why is there no formula I can write for that? The reason there's no formula I can write for that is the only way of expressing the strong force. I think the strong force on this scale is mediated by what's known as pions. I mentioned those earlier. We can have a couple of different types of pions. I believe the positive and negative types are their own, each other's antiparticles, whereas the neutral pion gets an antiparticle like that. I don't remember everything precisely. It's been a long time. Actually, I think I definitely mucked something up on the diagram I did earlier. Because yeah, anyway, moving on from ninja mucking stuff up. The point is that somehow the force between these two things, I'm saying, is being mediated by these. What does that mean? Well, what that means is that the only way physicists have ever worked out of describing the force between these two things is to say that one of them sends a pion one way and the other kind of sends it back. This is not rigorous. I don't know the exact things involved, but what Richard Feynman came up with was a way that we could say, okay, the neutron is here. Oh, maybe I do actually remember something of how this works. Okay, it's been a while. Okay, yeah, sorry. The neutron's down here, goes up here, sends something across, and maybe that thing actually swaps the place of what is the neutron and what is the proton, which sounds really weird. I don't remember if this is the exact interaction that's going on. But it sends across this pion. Maybe it's pi naught. You may have realised by this stage I don't know. These are a lot of specifics from particle physics that I'm no expert in. But it sends this thing across. But that's not the only thing it can do. If you look into it a bit further, you find out there are other more complicated things that can happen here. Perhaps at the same time you can get the emission of a photon going over here. They're normally denoted gamma in this, which I'm aware is confusing given my gammas look exactly like the news I used earlier for representing electron neutrinos. You can get a photon given out, or maybe you get a photon that even forms like a loop midway while it's travelling, but that doesn't matter. And that's the brilliance of Feynman diagrams. Only the first and simplest diagrams matter, but you may be seeing that that's exactly equivalent to what I was saying earlier. It's exactly the same thing as the waves in my sea of molecules in my saucepan, the pressure waves. Effectively, they're the same as audio waves. Those waves propagating across, they're no different. The way you analyse them is exactly the same. And what it turns out the quantum field theory states is that actually electrons, they're just oscillations. They are just oscillations like we had before of some underlying field. That is all an electron is. And this might seem strange, so I mean there are various pieces of evidence I can give you. For starters, it's only really possible to link these two up properly if you accept that, and in linking those two up into quantum field theory, you actually got the prediction of E+, the positron, which was then later experimentally verified. But a really neat way of looking at this comes back to the initial question. Because I told you electrons were fundamental. However, why can't I do this? Seems like a perfectly natural thing to be able to do. Why should you take it on faith from me that everything else is divisible, but suddenly electrons are indivisible? I cannot split an electron up into two parts. I mean, atom literally comes from the Greek atomos for individual. Originally, I'm trying to remember, Democritus maybe? Was it who named it? Don't remember. Who first came up with the theory of atoms, or the theory of indivisibility. That's what atom meant, but we broke it. But no one's yet ever seen an electron break. And quantum field theory predicts a lot of things, and it also explains why this is. Because what it says is that electrons are not particles. Electrons are just waves on like waves on a guitar string, actually would be the best example. This is going to sound a lot like string theory. It is separate, I promise. Electrons are just waves on a guitar string, but a guitar string can only oscillate in a certain... That was a pretty darn good sine wave. The next one isn't going to go as well, yeah. It can only oscillate in a certain number of waves. In particular, it has to be confined at both ends, because that's how the guitar's tied down. Which means you can only have waves that go a certain number of times. I can't, for instance, have a wave that doesn't quite make it back by the ends. That just isn't a wave that can exist on this guitar string. I can only have n equals 1, n equals 2, n equals 3 waves. But if we return to our analogy of considering phonons moving back and forth, considering the collisions moving back and forth between particles, these are called by physicists phonons. They are known as quasi-particles because they are particles which exist in, I guess, a medium which we understand to some extent. That might be a definition for them. I don't know the precisely rigorous one. But so what with these phonons, if we return to that, we considered these as, I described these as probabilities. But what happens if I add more and more waves? What happens if I add more and more wave packets into the system? Well, the probabilities, the rarer events, they're going to increase. But what did that actually mean in terms of the waves I had to begin with? Well, what that means is as I'm adding more and more of waves that look like this on top of one another, well, I just get something that's double the height. So what I'm really doing is when I make the waves double the height, that means these particles are moving back and forth double the amount. That means I've put double the energy into the system. And so what we can really do is we can view adding more energy to the system as being like adding particles. When I add more energy to the guitar string, I'm adding a new particle onto the guitar string. And the reason why we can only have a finite number of electrons is because we've defined that there are only a finite number of electrons. Sorry, that was meant to be like a lovely conclusion. I just mucked it up entirely. It's not only a finite number of electrons. What we are describing as an electron, why there are only an integer number of electrons, why we never see half an electron, the reason why is the sort of thing we are describing as an electron is an oscillation that looks like this. Now, what you can show quantum mechanically is that these oscillations are bound. They can only exist in a certain number of energy levels. You can only have an n equals 1. Okay, that was awful. You can only have an n equals 0, n equals 1, n equals 2. Why did I go n equals 4? You can only have it in fixed numbers, and the reason why you can only have it in fixed numbers is actually mathematically equivalent. I'm not going to particularly describe it here because that then would get a little bit complicated. But it's precisely mathematically equivalent to my guitar string. That was meant to connect back up, but let's just say that's an example of where you can't have a non-integer number of non-integer plucking number, I guess, or number of points held constant excluding this endpoint. Well, you can only ever have an integer number of those. It's the same, and that's the reason why electrons, where there only ever are an integer number of electrons. Now, you might be sitting here being like, Ninja, you've just ranted. Why can't I change my pen? I'd like to be able to use my eraser, thank you very much. Please? No. No, the computer is taking control. I cannot use my eraser. It has decided this is too... There we are. Okay. For some reason I had to press undo several times for it let me. And so that's my answer to this question. It's the fact that anything, pretty much anything can be a particle if you're willing. Any wave can be a particle. More or less, you can define anything as a particle. Particles have a series of properties, which is that they interact at points. They interact in certain ways with one another. That's what a particle is. But we've seen that actually, these particles, what we think are particles, every particle in physics, this is true. Oh, no, I'm about to be attacked because I used the word true. I did not mean to mean true. It is true insofar as it models the universe. A perfectly good model of the universe, in fact, the best model anyone has ever come up with to date, says that particles are no more than the easiest way we have of understanding the universe. They simply make calculations easier. So, did I completely dodge the question? Well, not entirely. Because... Sorry, I had to put that back because what's going on? For some reason, help. For some reason, this thinks I'm permanently clicking, and I don't know why it thinks that. Stop permanently clicking. Okay. Yay. There we are, okay. Really, really great way to derail my train of thought. So the point is, the best model that we have come up with says the particles are no more than a way of viewing the world, and a way of viewing the world that makes certain calculations simpler. That is all an electron is. That is all a pion is. That is all a gluon is. That is all any of these things are. They're effectively no more fundamental than saying that, hey, the thing at the bottom of here looks very similar to the thing at the bottom of here. And that sounds like it's a huge oversimplification, or maybe it's a flat out lie. That is pretty much mathematically rigorous. They are the same thing. And so back onto the question of, have I completely dodged the question? Well, no, I don't think I have. And that's relatively, this is what interests me. Like, phonons, if depending on what we define as the size of a particle, well, phonons themselves, they have incredibly little mass. They're carrying thermal energy, which is tiny in comparison to what electrons carry. Or what, say, for instance, quarks carry, which is mass energy. So if you were to measure the size of a photon, you'd say it's far, far smaller than a quark. But maybe I'm missing the point entirely. Maybe the question is not about that. The question is about what is more fundamental. Phonons aren't necessarily physical particles. Like, just as I said an electron was described by an underlying wave, well, a phonon is described by motions in neighbouring atoms. And if we're talking about motions in neighbouring atoms, well, the atoms there are the fundamental thing. They're what makes up the phonon. So maybe there's still something more fundamental. Maybe the quarks, so those atoms are themselves made up of energy levels, which are made up of electrons, which are in turn, they're made up of electrons. So in some sense, that particle, that phonon, was made up of a series of atoms, which were made up of a series of protons and electrons, and therefore quarks. And maybe that was what was going on. But this is where I find something really strange comes in, and I'm not going to be able to do this complete justice. Far, far better explanations of this do exist online. I'd recommend checking out Science Click English's video on symmetry. It's a brilliant video. But a basic answer to this question comes down to this thing I said earlier, which was this. It turns out that we really like laws of physics which have certain symmetries. And we can think we more or less observe these symmetries in the universe. In fact, you can argue that, well, physics has to actually obey certain symmetries. In fact, in order for physics to be meaningful, it needs to make predictions about the future, which means that it can't vary in time, or at least if physics does vary in time, we have to be able to predict how it will vary in time. But then if we're able to make a prediction, then predicting how physics will vary in time, well, that's just adding an extra law of physics. That law has to remain the same if we're going to make predictions. Physics actually has to obey translational time invariance if the world is to make any sense, if we are to be able to have any predictive power. And that's a really powerful statement, because what it means is that any law of physics we come up with must have certain properties. And it turns out that there are a series of symmetries. These are known as, I'm going to get this wrong, I think it's this, I don't even know how you do it. I think it might be like this. I'm really no expert. The universe that we're in has a series of symmetries. And we might say it looks like this special orthogonal group. These include rotations, these include reflections, these include translational symmetries, these include, well, actually, I'm not 100% certain they do. Anyway, sorry, I'm digressing slightly. These include what are known as Lorentz Boost, so that includes increasing velocity, includes decreasing velocity, and also changing time and spatial axes in accordance with general relativity. It includes a list of symmetries that we think the universe has. And a really powerful thing is that this actually let us predict new symmetries. People did some really interesting maths on continuous symmetries and realised that the same thing underlying these symmetries that we observe is actually a far more fundamental group, and I think I am really not an expert on this, so take the qualitative stuff here rather than the precision. I want to say it's SU2. No, that's not right, actually. No, that's something entirely wrong. Basically, what we found out that there's or the maths predicted that if we were to have continuous symmetry, so that means a continuous symmetry is not just, why does undo so much? I just wanted to try and do the last thing I did, not several other things. That a continuous symmetry is one where it doesn't matter how far in this distance I try. A discrete symmetry might be, say I've got a periodic lattice, and it doesn't matter which lattice site I'm at, things look the same. But it's just taking me back to the same place every time. It's annoying. Okay, so I can't use undo for the rest of this. It's always good to know. So that's a discrete translation of symmetry, a continuous translation. But note that if I try to go somewhere in between two atoms, if I go here, well, that looks different to being at one of the atoms. At the atoms, as long as I take a precise step going from one atom to the next, everything's perfectly symmetric. But if I ever exist anywhere in between, well, there should be an atom where I'm sitting, and there isn't. So what we expect is that the universe has continuous symmetries, but the thing that created all of those continuous symmetries we observe, there was predictions that, well, it should create some other symmetries, and these symmetries should be related to something really strange known as spinors. And these spinors are strange things that when you rotate once, so normally 360 degrees is a complete rotation, and you get back to where you started. Rotating by 360 degrees should leave you exactly where you are, but these spinors, these are strange mathematical objects that rotate 180 degrees, and they go from plus to minus, and this is really weird, but you rotate them again and they go back. So you have to rotate them 720. You have to rotate them 720 degrees to get them back to where you started, not 360. And then these strange mathematical objects, like, surely nothing like this can ever make sense, possibly in the universe, and they still exist. Called electrons. Electrons wouldn't behave the way they do in atoms if they didn't have this strange property that when you go 360 degrees, you get back to the negative of where you started with. It's an incredibly strange property which I can't make sense of. I have yet to see an intuitive explanation of any of this. It's just something taken for granted. There are kind of examples of where people will... There's a belt analogy of how you hold a belt, but realistically they're just saying, oh, here's this thing which, when I rotate at 720 degrees, comes back to the start. But you're connecting it up to something else. It's not a simple system. And so, yeah, it's, to my knowledge, like an actual understanding of these, they're about as well understood as complex numbers were pre-complex analysis. They're a tool which exists and which explains the universe, but they let us do something amazing. They let us... You can actually see them coming up before in these solutions for electrons, and they give us a huge amount of explanatory power about the world. And so people began realizing, well, if we look at the symmetries of the universe, and they began taking a look at this symmetry group. I'm just going to call it G because I don't remember what it is. And this is a mathematical entity which describes every single symmetry we observe in the universe around us, including this really strange one related to spinors. And it just takes all of these, it describes them, it describes what we can do. And by breaking this down into smaller and smaller chunks, people can effectively come up with... These small chunks are things that are invariant. Oh, okay, this is where the math gets complicated. Effectively, they break the group up into small chunks, and it turns out that these things underlying these symmetries are equivalent to particles. And so, the question you're asking me, Avery, is the following. Do I believe there is anything more fundamental than an electron? And my answer is that I do not expect anything will be discovered. Because aside from aside from like this weird bit, which is quantum gravity, I know I've drew two diagrams which looks like this. Aside from this one diagram, which is this one thing which is quantum gravity, which I'm not convinced personally we will ever be able to probe because the conditions are too extreme. If we could probe them, then the energy we'd have, well, we'd have potentially solved the world energy crisis. I'm slightly exaggerating, but the point is these things could always exist at higher and higher and higher energies, and so we would need to overturn a lot of physics in order to discover a new particle. A new fundamental particle in the sense that it is predicted by these symmetry arguments. We need to overturn a lot of physics. Now, that's not saying the physics couldn't be overturned, but the question is, what benefit would overturning it give? The model we currently have reproduces everything exactly. Even if I came up tomorrow, okay, not exactly, a couple of caveats there, but those. In short, I feel like a lot of the outstanding questions in physics are questions of emergence. They're questions of how something really simple, say, like a chain of atoms. Oh, I pressed Control-Z. They're questions of how something as simple as a collection of atoms can gain consciousness, effectively. They're this incredibly complicated, I'm not saying words that make sense. It's getting late, and I'm sure you're tired of this video by this stage anyway. They're questions of how seemingly simple systems can give rise to incredibly complex behaviour, like having a series of atoms, and giving rise to this incredibly complicated maths that I couldn't describe. Could there be a particle more fundamental, I'm going to say, than the electron? You could pick other things, and the answer is that to the best of our knowledge, no, there couldn't be. There are things you can overturn. So special relativity did this. Special relativity took the unsolved problem, or took an unsolved problem, the unsolved problem of some strangeness in electromagnetism. It took that and it gave us an update. We went from a group, which I'm going to call small g, and we moved over to a group big G. And suddenly this new group had incredibly more predictive power, and it simplified our understanding of Maxwell's equations. Maxwell's equations being a fundamental set of equations which more or less describe the universe, or the universe from an electromagnetic perspective. And I'm now writing them all out. And the interesting thing is there were these two different fields in these equations, and the differences between these two different fields were strange, and their interaction gave rise to light, which propagated without a reference frame. And this was incredibly weird. It didn't make any sense, and I've nearly finished writing all these equations out now. Oh, and I was about to press Control-Z, because I just do that automatically. That would have sent me too far back, and there's going to be it's a bit of an exercise, see if I can remember that. For anyone who's seen different forms of these equations or wondering what this one is, this is the vacuum form of Maxwell's equations, which is my personal preferred form. Yes, I do have a personal preferred form of Maxwell's equations. Find me. But they realised that actually this electric and magnetic field, they were actually just artifacts of what symmetry we'd chosen. If we imagine we're on a roundabout, it feels like we're being pulled outwards, and that's because our arms are being pulled outwards, we're being pulled away from the centre of the roundabout, and that's because of a force known as centrifugal force. It's a function of the fact you're rotating when you expect the laws of physics to behave as though you're static. Or not as though you're static, but as though there's... How exactly do I phrase this? Basically as though you're not spinning around. And suddenly when you spin around, you get a new force. And it turns out that, well, that's actually all that magnetism is. Magnetism is just an effect of the fact that we were working in the wrong reference frame all along, and that special relativity was the true reference frame. And maybe there's going to be a reference frame that will explain some currently unsolved problems in physics. Personally, I think most of the large unsolved problems in physics at the moment are questions of emergence or questions of reaching high enough energies to probe things like quantum gravity. And so I don't think we're ever likely to get an update to this group. We might do. I can't rule it out, because to say we've arrived at the fact, we've arrived at truth, is the fundamental flaw of physics. I can't rule it out, but I don't think that's the most likely thing. What I think is more likely is that we have an assumption. We have an assumption in physics which I can write something like this. This is a way of phrasing what's known as the principle of least action. Principle of least action is how we understand physics. I have a t-shirt which has something on it which is L equals and then a ton of stuff, and this is known as the standard model. I've seen a variant on this t-shirt which is "and God said let there be," and God said let there be light, and then have this equation beneath it, etc. I've seen various versions of this t-shirt, but the fact is that this weird thing here, this is something known as the Lagrangian, and what our current understanding in physics says is that in order to decide what happens, what truly happens, I need to define a quantity S. I mentioned this earlier. I didn't define it. I didn't explain what it was. This is where it comes from. This is where it arises. I need to take this thing L. I need to integrate it with respect to time. So I need to consider a particle moving in a certain way. Let's say I've thrown a ball and I wanted to get from A to B. And how do I decide which path it takes between A and B? Well, I could have taken maybe this path. Could have taken this one. What it turns out is that when you create this quantity called the action, when you create this S and you define it like this, someone discovered, I think Hamilton arguably first discovered that, oh no, this shouldn't be a dx, it should be a dt, discovered that when you work out this quantity, you evaluate it for every path, magically, somehow, it always seems to be the paths where this is minimized, or actually stationary in certain contexts, but let's say minimized. And that just seems to be true. And it turns out that this is actually an incredibly general way of writing lots and lots of equations. It can be an incredibly powerful tool, but it's worth noting that's just something we observed. We observed that S is equal to this. And we observed that if we defined this, if we defined L correctly, L takes the symmetries of the universe and other stuff, and we define L correctly, and we do this weird mathematical thing, and we find the minimum of S. That seems to be what the universe does, and there's no good reason for this. There's no good reason we should believe it to be true. This happens to be very general, but it's not completely general. It doesn't describe every single possible system. In fact, I can come up with an incredibly simple system that it doesn't describe, which is that of a pendulum connected by something which has a finite amount of friction. It can't describe that. Now, that seems not to be an issue because time's invariant, but I can come up with more and more interesting systems. And actually, shout out to Darwin, another one of the developers, for getting me to work on, working back on a problem I'd looked at ages ago, which is what is the length of this side of a triangle? Well, obviously Pythagoras tells us it's square root of a squared plus b squared, but what if we define that differently? What if we said that actually the length of this is the magnitude of A plus the magnitude of B? What would happen? What would happen if every single law of physics, where normally most physicists would write R, what happens if every single law of physics suddenly used, rather than R equals square root of x squared plus y squared plus z squared? What happens if suddenly we now used this new quantity? And you can start playing with the maths of that, and it doesn't work. You can't really do it because there are multiple paths which have the same there are multiple paths, to, if I'm being rigorous, infinitesimally close to one another, there are multiple paths which have the same action. All of these paths look identical, at least if you're considering a photon travelling along them. So there are laws of physics, there are universes which cannot be described by this. There are hypothetical universes, and what's to say that ours isn't one of those? We don't know that this is true. All we know is that this is the best model we have so far. And so the question is, what do I think will happen in the entirety of the future of physics? And I'm going to go out on a limb and say that I think the universe around us can be described pretty adequately by this. There are unexplained phenomena, but I am willing to believe that many of the unexplained phenomena we observe today are caused by this idea of emergence. The idea which gives rise to things like Conway's game of life, where you take an incredibly simple set of rules. Maybe you take Maxwell's equations I wrote before. Maybe you take atoms in a saucepan repelling and attracting, and you get incredibly complex behavior. And the universe is filled with this, and I feel like more and more the things we're seeing which can't be explained, I think can probably be described as emergent properties of the system. This could be wrong. This could be completely wrong. This is the point where I diverge from actual physics to my gut feeling, which is that I think the answer is probably no. Because even if we did go to a new group representation, I think it would be incredibly unlikely that we would get something that looked exactly like double an electron. I don't think we would. I don't have mathematical rigor behind it, but that feels like it would be a huge coincidence. It feels like we get something that will look completely different from an electron. I guess that's maybe illogical to say, because we've observed electrons, therefore we could only have things which gave us electrons. So, maybe. But I suspect that we would be more likely to see new particles. And so, anything smaller in the sense of really smaller, well, no. I can make photons which are arbitrarily low energy. Neutrinos are lower energy than quarks. I'm using energy and mass equivalently here because they are equivalent. Yeah, there'll always be smaller stuff in that regard. We can always define smaller stuff because that's all particles are. They're our way of looking at the world. But if you're asking me if there's something more fundamental, then I think we're more likely to be wrong about physics on a fundamental level than we are to find something smaller than a quark. Even stuff like string theory, etc., is not exactly positing a smaller particle. And the issue is that when you get to what is fundamental to a field, what underlies fields, the issue is that you're not talking about particles anymore. We haven't been talking about particles in a true sense for ages. The smaller and smaller you get. We're just talking about fields. Do I think these fields are something physical? I have no idea. I don't think there is an answer to that. Physics, I think, is necessarily always going to be incomplete. There will always be the question of why, which we'll never be able to answer, because realistically, there is one truth. Cogito ergo est. I like to joke because cogito ergo sum was the phrase stated by René Descartes, which is I think therefore I am. I'd argue that it's not so much I think therefore I am, it's that I think therefore something is. I know that in the extent to which I personally have defined existence, there exists something. The one truth of the universe can be written in formal mathematical notation as this. This isn't an E. Well, it is an E. But anyway. Is it that way around? I think I've actually mucked that up. I'm fairly certain it's this. Yeah, that looks a lot nicer. That's the fundamental truth of the universe, as far as we can tell. And yeah, physics will always be incomplete. We will always have, unless, like, physics can't solve this. Philosophy might be able to. Physics can't, I don't believe. And so, yeah. Remember, kids, physics is only a model. It's an incredibly powerful and incredibly good model, but that's all physics will ever be. It's a way of making guesses about the future based on what we think has been the past. There are lots of other questions that Avery asked. Avery and a guy called Mater, although not that Mater, sent rather a large number of questions, and I do intend and do want to go through them, but, well, yeah, I'm not 100% certain how that's going to go at the moment. I do want to do something like this on them, but also I feel like this is possibly not the best format to do it in. Anyway, that's my answer. I don't believe there will be something more fundamental found, because that would require effectively physicists to find something which still predicts things that look like particles, but which also happens to predict exactly half an electron, exactly half a quark, or something more fundamental. I see this as unlikely. It's not as simple as just breaking something down into two of what it was. It would be completely rewriting our understanding of the universe. We would have to throw out an incredible amount of science. It's not impossible. It's definitely not impossible. If there's one thing you should never, ever believe, it's someone saying a science is done. Which is a kind of what I'm not saying that, but it's my argument is that effectively I think new laws of physics are only likely to come at the moment from probing stuff. And I think that's incredibly exciting. I believe emergence is incredibly exciting, and that actually more physicists investigate emergence, the more we find things which are incredibly important to our day-to-day lives. So yeah. Thank you all for listening.